So having talked about proof by contradiction and proofs involving existence and for all statements, existence and uniqueness, we're going to look particularly at how to approach statements in conditional form. So an if P then Q statement, how are you going to prove that? And there's two ways of proving that sort of directly. The direct proof is just basically based on modus ponens, and the proof by contrapositive is based on the equivalence of the contrapositive. But also a common approach is to prove these statements using contradiction. So we'll look at all three of these, but remember the contradiction is just a specific instance of a contradiction proof. But I think it's interesting in the case of an if-then statement, the form that takes, and so it's nice to see that structure sort of separately.
All right, so the first approach to proving a conditional, the direct proof, is based on the truth values of a conditional statement if P then Q. So as we've already seen, if P then Q is vacuously true, ooh, I don't know if this makes the best handwriting form, if P is false, right? So if P is false, the statement's always true. Don't really need to worry about that. The only way that the statement could be false would be if P is true and Q is false. So all we have to show is that every time P is true, then Q is true to prove the statement is true. So we need to show that if P is true, then that implies Q is true. Okay, so that's the basis of our direct proof. So it goes kind of as you'd expect. We're going to suppose the statement P is true. And then we're going to create some sequence of logical equivalences and implications until we show that that is enough to prove Q. And that will do it. So it's pretty straightforward proof. Some things to note: for a direct proof, you're going to be working with the premises P and concluding the conclusion Q, just as they appeared in the statement. So if the premises P are easy to work with and the conclusion Q is an easy place to get to, then the direct proof is a great approach. Proof by contrapositive is based on the equivalence of the contrapositive to the original statement. So that's logically, we know that the conditional if P then Q is equivalent to the contrapositive statement if not Q then not P. And so proof by contrapositive proceeds by proving the contrapositive is true, which will then prove that the statement is true. So it's basically a direct proof applied to the contrapositive. You're going to suppose not Q is true. That's our starting assumptions. Once again, you're going to build your chain of logical implications and or equivalences until you show that not Q implies not P. And then you'll say something like, thus, by the equivalence of the contrapositive, right, P implies Q. And you are done. So unlike the direct proof, where your starting assumptions and premises are P, in proof by contrapositive, your starting assumptions are not Q. And so this is going to give you just an entirely different set of assumptions to work with, as well as a different ending point, not P instead of Q. So if you found P and Q to be difficult to work with, maybe not Q and not P are easier to work with. So that's how you're going to decide between these two techniques. Finally, if we're doing proof by contradiction, I'm missing an N here, that again, it's just the contradiction proof applied to a conditional statement. So we know proof by contradiction, we show that not R is false. So we show not R, and that's equivalent to R. So we want to show not our conditional, if P then Q, and we want to reach a contradiction with that. So what is that structure going to look like? So suppose by way of contradiction, not if P then Q. But what is not the conditional? Not if P then Q, we've shown is equivalent to P and not Q. And that's the form we're going to use for our supposition or assumptions. So suppose by way of contradiction, P and not Q, and then, once again, create your series of logical implications and or equivalences until you reach some sort of contradiction, and you can say, thus, it follows if P, then Q. And we finished our proof. So this is what a contradiction proof is going to look like in the case of a conditional. Now note why contradiction proofs are so popular. What do I have to work with in this proof? I have P and not Q. So I have the premises of both my direct and my contrapositive proofs at the ready. And it's always easier to prove things if you have more assumptions to start with. You know more to start with. So there's more directions you can go, more things you can use. So you've basically doubled what you can start with. You also have sort of untethered your endpoint. You're just headed towards a contradiction, and any contradiction will.
Sometimes not knowing what contradiction you want is a little intimidating. It's like going out for a hike and not knowing where you're going. Then again, you don't have to get to a particular waterfall. Any waterfall you get to is a success. And so it sometimes is easier. So that's why proof by contradiction is often the approach when you get stuck doing proof, a direct proof or a contrapositive proof or any other proof approach that's just not working for you. Then contradiction might be the way to go.
All right, so let's look at an example of each of these proof styles for a particular proposition. So here we have the proposition, if n squared is odd, then n is odd. So one thing, you should always start your proof by really making sure you understand the proposition. And the steps to really understanding a proposition are simplifying any negations, don't see any negations here, and identifying any hidden quantifiers. And basically just diagramming the structure of the statement so you really recognize what this is. So we clearly see the if-then form of the statement, right? So if I use P to be the statement n is odd, or n squared is odd, and n is the statement n is odd. So again, P is n squared is odd, Q is n is odd. I don't think I said that right the first time. Then I have my classic conditional if P then Q. But there are hidden quantifiers here. The definition of odd is defined on the integers. So really, the assumption is that n is an integer, and then we have to interpret what is intended here. But there's really nothing to imply that we're claiming this for a particular integer. We're not saying that there is some number n out there such that n squared is odd. If n squared is odd, then n is odd. I think the implied claim is that it's true for all n. So it probably would have been better form if we had written the proposition explicitly saying for all n in the integers, if n squared is odd, then n is odd.
This happens a lot in math where we kind of assume it's arbitrary unless stated otherwise. So there's something to look out for. If we don't specify otherwise, assume it's arbitrary.
All right, so we see in this example that this is going to be a for all proof. So as I said before, a lot of times you have these nested forms of a proof. So dealing with the for all statement true, let's do a direct proof with this for all. So what's the proof going to look like? Well, at the mile high level, we are doing a for all proof. So we are going to instantiate Rn as an arbitrary integer. So I'm letting n be an arbitrary integer, and then I need to show if P then Q. So I need to show that if n squared is odd, then n is odd. And then I can do universal generalization to say, therefore, since n was arbitrary, it follows that for all integers n, if n squared is odd, then n is odd. Sorry, handwriting here is getting pretty messy. Okay, now what goes inside, nested inside this for all proof is a conditional proof. So here's my conditional proof inside. And if we approach this directly, as a direct proof, I'm going to do if p then q. So I'm going to suppose p. So let n be an arbitrary integer and suppose n squared is odd. And then I'm going to need to create some set of logical implications or equivalences that help me assume or help me show n is odd. Okay, and that will have verified my if p then q part. So we see that conditional proof nested inside the existence proof. Or sorry, the universal for all proof. Okay. If I was going to do the same proof by contrapositive, let me just start with this. It's still a universally quantified statement that I am trying to prove here. I'm not giving myself a lot of space. Okay, I'll write it again or move some things around. Okay, so I'm still trying to prove this universally quantified statement. But I'm going to change how I do the inner conditional proof. So this time we're going to do the inner conditional proof by contrapositive. And so for contrapositive, we're going to, as we said before, suppose not q. So what is not q in this statement? We're going to suppose not q, and we're going to try and deduce not p. Okay, so what are those in this statement? So the statement not q, I'm negating n is odd, and since every integer is either even or odd, okay, I know there was some question on whether 0 is both even and odd or neither. No, 0 is even. 0 is an even number. So every integer is either even or odd. So saying that n is not odd is the same as supposing n is even. And similarly, the negation of the statement that n squared is odd is that n squared is even. Okay, so if I wanted to do this particular proof by contrapositive, that would be the form of the conditional proof nested within the universal statement. Now let's think about which one of these we would rather work with. Here, I get to start with something about n and conclude something about n squared. Okay, so going from n to say something about n squared, how do you feel about that? Here I'm starting with n squared and trying to do something about n. So I hope that you recognize that it's much easier to start with n and say things about n squared than it is to start with n squared and say something about n. Generally speaking, if I start with n squared and wanted to deduce something about n, that would involve a square root, which then I'm getting dangerously out of the realm of integers, and it's just a much more complicated process. Furthermore, there's really nothing inherently easier about working with odds than evens. So since it's easier to work with n, and evens are just as easy as odds, this looks like a much better approach for this particular statement than a direct proof would be. Okay, what would the statement, or what would the structure of this proof look like if I was doing proof by contradiction? So this is something to note. Whereas both the direct and the contrapositive proofs were nested within the same for all proof structure. Because contradiction is a universal approach to the proof, I need to negate the entire statement. So let's go back up here and look at the statement. I'll write it symbolically. Okay, so my statement was, my proposition was for all n in the integers, n squared is odd, then n is odd, right? And this was my if p, then q. All right, so I'm trying to negate, I'm going to suppose, so proof by contradiction, I'm going to suppose not R, where this entire statement is R. Okay, so let me write it all symbolically, and in Z, this whole thing is R. So what is not R, right? If I negate this whole thing, I have to first negate the quantifier for all n in Z. Okay, so the negation of the statement R is going to be that there exists an n in Z such that, and now I need to negate, I'm negating this entire statement, okay? That's my not R. Okay, so this is R, then not R, running a little out of room, not R is going to be the negation of the universal quantifier, which is an existential quantifier, and then it's the negation of if P then Q, which, as we already said, that is equivalent to P and not Q. So I'm going to suppose that there exists an n in the integers such that, okay, P was the statement that n squared is odd, and Q was the statement n is odd, so not Q is the statement n is even. So again, we see that I get to start with both assumptions of the direct and contrapositive proofs, and I just need to reach some contradiction